In this section, we will learn how to compute limits. Okay, last time we learned the intuitive meaning of the limits. Today, we will learn how to compute it. So the first situation where it is easy to compute is when we are dealing with functions where we know already they have their limits. So we need just to so if the new function format is composed by many functions, and if each of those functions we know to compute it easily its limit, then we can use algebraic operations, as you can see here. So if we know that the limit of f is L1 and limit of g is L2, then the new function f plus g or f minus g has a limit. We prove using the definition that it is just you add the limit of each function, or if the difference we are interested with the difference, we do the difference. Also, the product of the two new function, the function product, its limit will be the product of the limit of each of the functions, limit of f times limit of g. The limit of the ratio function will be the ratio of each limit, but it is true. We establish this equality under this condition. We must check that the limit of g is different from 0. Okay. Also, using the precise definition, we can establish all these equalities also when we deal with the one-sided limit to the right or limit to the left of x0. Okay, so a simple example of we can have many examples for this. So for example, okay, sorry. So an example, let's consider, we can imagine an example. For example, if I look at this limit function 2x2 minus 1 plus 1 over x, okay, as x approaches 1. Okay, so I look at my function. So my function, as I see it, I can look at it as a sum of three functions. Here, a product of a constant function times a polynomial x2 power function, add a constant, then plus 1 over x. So a ratio of two functions also. Okay, so you see, so we can use the theorem here, the property we explain it here. So I have when I have a sum of two functions, or I know each of the limits, so I can say, and here I know from the beginning the constant function approaches itself. 1 over x, yes, as x approaches 1, x approaches 1, so it's different from 0. I can divide. This is a constant function. For the numerator constant function, x approaches 1. So yes, I can use the theorem and write without I can say first I have a difference of there's two functions, then a sum and another function. Okay, then I say I have limit of 2 times limit, I use the properties, okay, minus limit of 1 plus limit of 1 over limit of x. Okay, and then so this one is 2. This one I can see it as limit of x times limit of x. Okay, minus limit of 1, we said it's a 1. Okay, so it's 1. Let's move here and let's continue here. So limit of 1 is 1, limit of x as x approaches 1, it's 1. So finally, yes, it will be 2 times 1 times 1 minus 1 plus 1. Okay, so it will be 2. You see? So And more generally, so in general, we have this property, which is always true, limit of a polynomial, or yes, polynomial, as x approaches x0 will be p of, like you are substituting the value, and the limit of the rational fraction px over q of x as x approaches x0 will be limit of p of x, so it will be p of x0. Okay, we substitute the value. Okay, so it will be p of x0 q of x0. Of course, here we are dealing with the situation q of x0 different from 0. So as long as you can compute this the limits, they are finite here. These numbers are finite numbers, means when we say that it exists, then that means it is a finite number. Okay, L2 also is a finite number. Then you can manipulate these limits or these operations. Okay, so which is good. Now let's see other situations where the situation is more complex. So sometimes when you compute the limit, you have a problem. You have a situation like something infinite over infinite, infinite minus infinite. These are called indeterminate forms. So so the idea of how to compute the limit, then you will see. So let's look how we will do it through an example. Okay, let's consider the following example. Okay, so let's consider this example. So if I try to look at this function as the ratio, so I can substitute the limit of x2 will be x0, and numerator here it will be square root of 0 plus 9, which is square root of 9, which is 3, minus 3, 0. So I have an indeterminate form like this one. So I have my function behave like 0 over 0. This one we cannot say that the limit doesn't exist, but we can say also that it exists. Okay, so small quantity over small quantity, we cannot say, we cannot control it, which one is smaller than the other one, and what is the behavior at the limit point. Okay, so the idea is to work, how to overcome this difficulty is to work on your expression first before taking the limit. Transform the expression. Sometimes we can so overcome the difficulty. So that's why you need to practice more in this situation, on different situations, so that you get more recipes. Okay, so it's more recipes. You need to know some recipes. Okay, so when we have the square root, usually we think about the conjugate expression. So we a conjugate expression of square root of a plus b, like that, is square root of a minus b. So the idea is to multiply an expression like that with something like that. Okay, so I will multiply x2 plus 9 minus 3 by its conjugate. So the conjugate will be x2 plus 9 plus 3. Okay, let's erase this part. Okay, now let's continue. Now, since I multiply the numerator by this factor, so I will multiply also the denominator, so that I don't change my function, original function. Okay, I keep the same function, working on the same function. Okay, now let's develop the numerator. I see I have that something like a minus b times a plus b, so it's a2 minus, so a minus b times a plus b. Remember, it's e2 minus b2. Or you can just develop and simplify. Okay, you don't have to memorize everything. So we will have square root of x2 plus 9 square minus 3 square over so x2 and square root of x2 plus 9 plus 3. Let's continue. Okay, so its limit as x approaches 0. So the square root to power 2 will give me x2 plus 9 minus the 3 power 2 is 9. Okay, over x2 and square root x2 plus 9 and plus 3. Okay, so let's continue. I see now that I can simplify by 9, and I have now x2 at numerator and x2 a factor, common factor, so I can simplify it again, and my new function will be something like that. Okay, and now let's try to take the limit. So from the beginning we didn't we didn't take the limit, we just worked on our expression. So even you can work just without using the symbol. Okay, so now if you take the limit, you see that the denominator is no more causing problem. You can take the limit exists. So you can at this level you can use the algebraic uh, op operations. Okay, at this level we can use it, and you will get 1 over. So when you substitute 0 here, you have square root of 9, which is 3 plus 3 will be 6. You see, so we could use at this level. Okay, so this is what we expressed here. If you look at this theorem, it says that if you can write your function differently, where x is different from x0, so you are close to x0 but not at x equal exactly at x0, and the new function has a limit, then the original function has the same limit. Okay, at this point. So this is how we overcome yes, we overcome indeterminate forms, or yes, or not necessarily indeterminate forms, like this situation. For example, this example, here is my function. I don't have an indeterminate form. I want to compute the limit, so I'll start. I'm asked to compute limit of fx as x approaches 1. Okay, so I am approaching the concept of limit is when we approach the value without touching the value, without looking at what is happening at exactly the point. So when I am far from 1, here is I am here. When x is different from 1, my function is equal to x plus 1. So I can say it's equal to the limit of x plus 1. This is it's not my new function, it's my function, but it is given here like that as x approaches 1. And now this function, we know how it's sum of two functions, one constant, function x when x approaches 1, so it's 1 plus 1, which is 2. Okay, and this is my limit for my function. Okay, great. Okay, now another thing, so you had that. So the first thing we saw the algebraic operations. Second, situation and determinate forms. So you need to work on the function, find new expression where you can do the algebraic operation. Another situation is where we use comparison. Okay, we use comparison to conclude about the limit. It's hard. We can't use algebraic operation, we can't remove the indetermination, etc. So the idea is to compare f with two functions, and each of these functions has the same limit. Then necessarily we prove that the limit between the two functions is we necessarily have the same limit. So its limit exists and it is exactly the same. So let's see how it is through this example. Okay, so we are interested here at 0. You see, 0 is causing problem here. 1 over 0 is 0. No, I mean 1 over 0 is infinite. It's infinite. Sine now of an infinite angle. If you remember, sine function is a function that is oscillating. So when x takes large values, still my sine function is oscillating, is not approaching any value. We prove, but it's not at the level of this course, that the limit of the sine function at infinity doesn't exist. Okay, so intuitively we understand. Okay, so here we see, you cannot conclude. You see here x2, yes, approaches 0. It's product of two functions x, and yes, it's 0, but here the limit doesn't exist. So how can I explore this the behavior? Okay, so let's try to compare. This is not our fx, we wanted to compare it. So here is the idea, here is the comparison. We can do this comparison here. Okay, so sorry, okay, so okay, so here is set, yes. So I will take the absolute value 1 over x. You will see what I'm going to do. I know the properties of the absolute values. It's product of the two absolute value. Okay, absolute value of positive number x2 is always positive, so it will be x2. And here the absolute value, so sine is changing sign, it can change, but I know something. I know that the absolute value of sine of an angle is always less than 1. Okay, so this quantity is less than 1. Okay, is less than 1. Okay, so we can deduce then the whole quantity is less than x2 times 1. Okay, and then you can say that x2 sine of 1 over x is between minus x2 and x2. So here what I use it, something maybe you don't remember, that we say that absolute of a less than a is equivalent, that you say that is between minus a and a. So this is what I did. I have this less than x2, then this quantity is less than x2. Okay, then the inside of the absolute value is between the x2 and the opposite. Okay, and now clearly the limit, you see, now this function, I know that it approaches 0 as x approaches 0. This function approaches 0 as x approaches 0. So my limit of x2 sine 1 over x will be 0 as x approaches 0. So this theorem, we call it the how we call it? It has a name. Don't remember. Comparison. The I don't remember. Some they call it sandwich theorem. Okay, it's not important. Okay, so but it's a comparison. Another way also, sometimes you need just to check if the limit exists or not. You can explore what is happening at the right and the left to the point. If the two limits doesn't exist, then the limit doesn't exist. They are different, doesn't exist. Because we saw that the limit of fx equal as x approaches x0, if you remember, exists if and only if the two limits from the right and the left exist. Okay, so for example, a practical example here. Let's see through this diagram. Let's make it smaller, bigger here. So if you look, okay, so let's see what we can do here with this limit. Okay, so let's explore the limit. Just there are many limits we can explore, but let's look at this function. Let's call it y equal fx. Okay, this is what our y equal fx, and we want to explore the limit as x approaches 0. Okay, but from the graph I see that my function is a piecewise function, takes different formula from the right and left of 0. So I will explore first what is happening from the left of f at 0. So now the formula of f here, I see it's the value 2, it takes the value 2, so it will be limit of the constant function. So here I have y equal 2. Okay, so the limit as okay, so it's 2 as x approaches 0 minus, which is 2. Okay, now the limit from the right of fx as x approaches 0 plus. So I have the linear function here that passes through 0, 0. So it's in the form y equal mx. It passes through 0, 0. As for x equal 4, we have y equal 3 for the line, not necessarily my function. So I imagine I have a line passing through 0, 0 and this point 4, 3. I'm trying to find the m, identify m. So m times 4. So m will be 3 over 4. So the equation is 3 over 4x as x approaches 0 plus, which is 0 also. It's 3 over 4 times its constant function times 0, okay, which is 0. You see, and you see now we see that the two limits are different, so the limit doesn't exist. Okay, from here we deduce that limit of fx as x approaches 0 do not exist because the two limits are different. Okay, they are different. Okay, great. Okay, now the last result, important result you must know is this particular limit of sine x over x as x approaches 0. So you are supposed to know this function, this limit, and you can use it in your calculation. And so the proof of this limit uses the comparison. Okay, so this is why it is important. It uses the theorem. So let's make bigger this sorry, okay, no, still bigger, sorry, sorry. So I wanted to give you an idea how it works. Sorry, that's why I'm touching. That's the good one. Oh, I can't make it bigger. Okay. So the area, yes, it shows. So let's maybe put it bigger like that. Another way to make it bigger. Yes, let's increase the size of the screen here like that. So how we prove this limit is by comparing areas. Okay, so area of we consider first an angle x with size x. This is the unit circle, and we are comparing this triangle inside the circle and the right triangle, this one. Okay, so we use the sine x, it's the opposite side over the size of the opposite side over the hypotenuse. Okay, so it's what we called it y0. Okay, and the cosine is the adjacent side over the hypotenuse, 1 over hypotenuse. Finally, the hypotenuse is equal 1 over cosine x. Y0 is sine x times the hypotenuse, and finally y0 is tangent x. So all this calculation is to show that the size of this side of the side of this triangle, okay, is tangent x. Then we compute the area of this right triangle. It's half this side times okay, the tangent x. So we have this quantity. Then the sector, the area of the sector, the area of the sector. So it's the sector area of the sector. I remind you, sector area. Sorry. Okay. Area of sector is sorry, area of sector. So it's half theta r square. Okay, so this is what you applied, half r here is 1 and x the theta, the angle. And yes, so just write, and the last triangle, half of the basis times the height. The height is sine of x, and we have exactly, this is 1 unit. Okay, and we compare having this this inequality, we express tangent x as cosine x over cosine x, and yes, and compare, use this inequality, discussing the case x positive and x smaller than 0 between okay, less than pi over 2 and greater than minus pi over 2, and we deduce the inequality. Okay, we deduce the inequality. Let's reduce the